All right, hello physicists. We're going to do a sort of a compressed unit this time. We have a test 1 week from today as I'm posting this, and homework is due this Friday, not next Monday. And so in this video we're going to try to cover most of the stuff that we're going to test over. We're going to cover standing waves, and we're going to cover the LC circuit. And these are these might not seem very connected, but the thing that ties them together is the idea of resonance and the idea of a standing wave. So the place that we're starting out from, where we got to on our last video, was that we had introduced this expression for a wave traveling along a string. Okay, so we have a wave traveling, it has an amplitude and a phase, and in this version, for instance, this K is traveling, this K is related to the wavelength. The wavelength is the length for one full cycle, for the distance from peak to peak, or from trough to trough. And then we also have, so that gives us a K in our expression for our wave. And then we also have our omega in our expression for the wave. That's this. And that has to do with our amount of time that it takes for, if we're just standing at one position, for the string to go up, down, and back. Okay, so T, the period, is the time for one full cycle. Lambda, the wavelength in meters, is the length of one full wave, the wavelength. And then we have to put factors of 2 pi in those to make this work nicely with the sine function. And so what we learned at the end of our last video was that we could talk about our speed in terms of omega and k, or more familiarly, just in terms of the wavelength times the frequency. And this is what physicists would call the phase velocity of the wave. Something we also discussed was the idea that if you have two waves that are traveling in opposite directions, they move through one another, and you get this. You can get the situation where you have some points that are not moving at all, and other points that are moving up and down and up and down. Now, something to be a little bit aware of. This is a snapshot of t equals 0. T equals 1/4 of the way through your cycle, half of the way through your cycle, 3/4 of the way through your cycle, and then once you're all the way back through your cycle, the wave looks exactly like the string looks exactly the same as it did at the beginning of the wave. One thing to be aware of is if you're looking at this just as a snapshot, it can seem a little bit puzzling, because you say, oh my goodness, where did all of the energy go? You know, we had that string stretched out, that would give it some potential energy, and then it's just flat. But what you have to realize is this series of snapshots is actually talking about something that's bouncing up and down. So at the points where the string is flat, that's where the string has the most kinetic energy. So this is the bouncing up and down of the string. Another thing that we discussed briefly last time was that we can sort of engineer the different nodes and antinodes that we want to see by by setting up different situations. So, for instance, in class, what we did was we used a long slinky, and one person holds the slinky really tight, and the other person shakes the slinky, and a little ripple goes down the length of it, and when it gets to the end, it bounces back below. So in this case, this would be like a positive displacement, and then this would be a negative displacement. And so if you do that a bunch of times and you add them together, those the sum of these incoming and outgoing waves can lead to your wave resonance or your standing wave. On the other hand, this could be different if you have a sliding, like a loop on the end. In this case, this displacement is above the equilibrium line, and then when it comes back, the hoop is able to slide up and down nicely, and so it also comes back above. So we're going to today look at different examples involving musical instruments, for instance, that employ this. What musical instruments do is you blow the air, and the different waves that go in there, the different changes in pressure, they all kind of happen together, but only some of them sort of add constructively in such a way that you get that constructive interference, that the shaking of the instrument leads the air to shake, which in the end makes your ears shake at a certain frequency in time. So how does that work? Well, remember the air having longitudinal waves travel through it. That's our picture of sound. We have the idea of sound having these different qualities, like the pitch. So that's your high pitch, low pitch. If you go up an octave, for instance, that's like doubling the frequency of the oscillation. Bum, 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 bum. So that's going up one octave. You're doubling the frequency. The wave amplitude has to be squared to manifest as volume, and it turns out it's a little bit more complicated than that. I believe, don't quote me on this, but I think it was Helmholtz who did the sort of psychological investigations of seeing what sorts of amplitudes register as loudness, and he found that it went on a log scale instead of a linear scale. So if you have a wave that's twice as, the pressure difference is twice as big, it does not register as twice as loud. It registers much less than that. So this formula for how many decibels a sound is, it depends on two things. It depends on this reference intensity that goes in the denominator right there. That reference intensity is supposed to accord with sort of the smallest intensity that you could register. And so if you're quieter than that, you probably aren't hearing it. And then the log in this scale is sort of on the psychological level of how loud do you hear it in terms of this intensity. The intensity, on the other hand, if we have, it has units of watts per meter squared. Remember, watts is joules per second. So this is telling us how much energy per second per meter squared is going through a surface. That surface, of course, that's important is your eardrum. So if you want to find out how much energy is being delivered to your eardrum, you would have to take the surface area of your eardrum times the intensity. But so you don't need big intensities of sound to be able to register it. Now, if you think about this in terms of a source that's emitting sound in all directions equally, then the intensity that it dies off with would be 1 over r squared. And that's sort of like, if you had like a little flashlight that, had a bulb that's just letting out light in every direction, and you go farther away and the light, the energy is spreading out in space, and so the intensity dies off as 1 over 4 pi r squared. 4 pi r squared, of course, is the surface area of this sphere. Of course, sound doesn't necessarily have to act like that. You could have, sort of a directed speaker or something like that could have a much more directional quality to it. You can even have things like sound lenses that can focus sound. But in any case, So we have the sound intensity, which for an isotropic source, which is letting sound off in all different directions equally, dies off as 1 over r squared. And we also have the decibel system, which tells us about how we register the intensity of sound. Okay, so I've given you a homework problem about this. Ignore the number. Your homework is a little different because, remember, this is a short homework. It's due on Friday. What does it say? It says the source of a sound wave has a power of 1 microwatt. Okay, so power is 1 times 10 to the minus 6 watts. If it is a point source, what is the intensity 3 meters away, and what is the sound level in decibels at that distance? Well, if you're putting in your power into this equation, right, your intensity would be that power, so it would be this over 4 pi, and I guess they have 3 meters away, so 3 meters squared. Think about what the units are here. It's watts per meters squared, because we have 3 meters times 3 meters down there. Okay, so watts per meter squared is our unit on intensity. Now, it asks us then, what is the sound level in decibels at that distance? Well, you're going to find this beta, that's your sound level in decibels, is 10 decibels. Okay, notice this already has our units on it, times the log base 10 of whatever you found here, divided by your intensity naught. So that's your reference level, your 10 to the minus 12 watts per meter squared. Okay, so the intensity you put up here has to have units of watts per meter squared to cancel out the watts per meter squared there. You take the log, you take it times something with units of decibels, and there you go, you have your answer. Now, you'll remember that I mentioned that when you do, just a sec, I'm going to actually grab my guitar for this. All right, yes, I forgot to bring my guitar downstairs. Okay, so here's the idea. If you have a string like this and you pluck it, not sure if you can see this or not, the first end and the other end, they both act as nodes in your standing wave. Now, if I put my finger on here, that can also make another node in my standing wave and force and it will encourage the resonance of my what we call the second harmonic. So that basically splits the string in units of 2. We could also split the string so that we have a node here and here. So here we're dividing the string into 4. So by putting these different nodes in different places, we can either change the length of our string, so usually you're hearing that first harmonic, but then you can of course put your finger down and hear different harmonics. And so like in a flute or something like that, you can encourage those different harmonics by blowing faster over the hole or what have you. Now, I am going to give you these sorts of formulas on a test, but I don't think they really are that useful. Because unless you understand what's going on in this, you're going to be lost. So let's just try drawing the picture, and we're going to draw the picture for the case of our open string and the case where we have where we have clamped strings on both sides like a guitar, and the case where we have opening on both ends, like in a flute, for instance, where you're blowing over an open end and then there's an open end on the other side. So let's say that you have 2 ends as nodes. Okay, So our example here would be a guitar. Well, what sort of resonance would we expect? We would expect to get a standing wave pattern that looks approximately like this. And so if this length is set and the speed of the wave, remember the speed of the wave is already kind of set by the tension and the linear mass density of the string, then we can go ahead and find out what the wavelength is from this, and then the wavelength with the addition of this V equals wavelength times frequency. Once we have that wavelength, we can find the frequency, and that we hear as the pitch. So in this case, for our first harmonic, we have 1/2 of the wavelength, because if I wanted a whole wave, I'd have to go like this. But I'm gonna erase that because the string doesn't extend out there. So 1/2 wavelength equals L, the length of that string. So how do I find the wavelength that goes along with? It's just 2 times L. Then the way I go from the first harmonic to the second harmonic is just by adding in a node. And every harmonic going up is just going to have one more node than the last one. So for instance, here we go, and we have added a node in the middle. Okay, now notice this is one full waveform, so in this case the wavelength is simply the length of the string. That's our second harmonic. And then if we wanted to go to our third, we only have one, we're going to have our nodes on the edges. We only had one node here, so we're now going to have 2 nodes. Okay, so now I'm going to draw in my waveform. Dash, 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 dash. And you'll see that this is one, each one of these up and downs is essentially half of a wavelength. So this is half a wavelength plus half a wavelength plus half a wavelength. So I have 3/2 of a wavelength equals L, or the wavelength is 2/3 L. Now, what happens if we have the two ends as antinodes? This is a case of like a flute. Well, in this case, you're going to have your maximum vibration out here and your maximum vibration out there, but to fit in one waveform, you're going to have a node in the middle. It's going to look like this. So in this case, notice this is, again, it's 1/2 wavelength is this, because we're going from maximum to maximum. We're going through a minimum, but we haven't gone all the way through. So this is 1/2 wavelength equals L, so the wavelength equals 2L. So all the equations are the same, but it means something different in this case. Again, instead of having one node, we're going to have 2 nodes. Whoops, let me dash one of these. And so in this case, again, the wavelength is just for this second harmonic. First, second, for the second harmonic, the wavelength is just the length of the tube, and so on. Okay, so that's two nodes, and then if we wanted to go to our third harmonic, we'd have to add in an extra node. So it'd be something like this. And just to keep it in mind, what the positive and negative things here, it just means overdensity and underdensity of air in the tube. So here we'd have one full wavelength plus a quarter would give us 1 1/2. So that would be 3/2. Wavelength equals the length, or just as before, the wavelength is 2/3 L. Okay, so just to drive this home, I gave you a homework. Ignore this number. I numbered them differently than is shown here. But it says you have string A is stretched between two clamps separated by distance L. Okay, so string B with the same linear density and the same tension as string A. Why is that important? It's important because that means that the speed of the wave is the same. Okay, is stretched between two clamps separated by distance 4L. So 1, 2, 3. 1, 2, 3, 4. Okay, then it says, consider the first 8 harmonics for string B. Okay, so that means when you do this homework, you're going to have to draw out all 8 of those pictures. For which of these harmonics does, if any, does the frequency match the frequency of A's first harmonic, A's second harmonic, and A's third harmonic? Okay, so here's A's first harmonic. Here's A, here's B. A's first harmonic is this. So it has length L. So the wavelength here is 2L. And since these have the same linear density, the same wavelength means that we want to have something, we would have the same frequency. Now, let's just draw a couple of these. I'll draw the first 4 or something for B. Okay, so there's the wavelength here. This is 4L, so the wavelength here is 4 times 2 would be 8L. So that's the first. If I wanted to draw the second, it'd be something like something like this. Okay, so this is 1.5 wavelengths. Sorry, this is 3/2. Whoops, what am I doing? I skipped a harmonic. I'm getting impatient. Okay, we want to, if we're going from the first harmonic to the second harmonic, we have to add 1 node. Okay, so that's 1 wavelength now. So the wavelength here is going to be 1, 2, 3, 4, 4L. That's our second. And if we wanted to draw our third harmonic, we're going to just put in 1 more node. So I guess this is going to be at 4/3, and this is going to be there. And so this one has 2 nodes. Okay, and so we get that 1.5, so 3/2 wavelength equals 4L. Or the wavelength is going to be 8/3 L. So that's right there. That's 1 wavelength. And then finally, here's our 4th harmonic, 3rd. And this one has to have 1, 2, 3 nodes. Oh, look, 1, 2, 3, and we can draw that in. Okay, and so we can actually just count out here our wavelength is going to be 1, 2, L. So there's our 4th wavelength equals 2 L. And I hope that you can see that this wavelength equals 2L and this wavelength equals 2L. So in that case, because the wavelength is the same and because the speed is the same, V equals wavelength times frequency. So frequency is going to be V over wavelength. So in this case, when we have the same wavelength, we're going to have the same frequency. And that's because we know that they have the same same linear density and under the same tension. Remember the V is that related to both of those. Okay, so the first harmonic of A has the same frequency as the fourth harmonic of B. A longer string is going to have those low harmonics much lower. Okay, you know that because if you look at like a string bass, it makes lower noises than a a little tiny fiddle. Okay, now the one that is a little bit, so we already looked at two open ends, and those have this essentially the same pattern except a different meaning as our two closed ends. What's a little bit surprising is that if you take that open tube and you put your hand on the end of it and then blow again, it will reduce the fundamental by an octave. It'll cut the wavelength in half. It will cut the frequency in half and double the wavelength. And to see why this is, let's look at the patterns. So here's your first harmonic. Now, the way they've numbered this is a little confusing. They say you only get odd harmonics, so you only get 1, 3, 5. But if you're just looking at this, I will try not to force that kind of language issue. But this here is just 1/4 of your wavelength is going to be L. So here, your wavelength is 4L. Okay, so that is a little surprising. Remember, the node is now one node is at the end, the antinode is at the other end, and so you can fit in a longer wave and make a resonance. Okay, same way with the other resonances going on up. Now, this is sort of an interesting case because whoops, I got again too hasty. Because one of the labs that I have done here at Centenary, and I did this one last year, and we just don't have time to do it this year. I might bring it back. It looks like this. You have a cup of a tube that's filled with water, all right, and you have like a rubber hose at the bottom, and you can lift a little cup up and down, and if you bring this down, it can make the length of the tube longer. And then what you do essentially is you bring a tuning fork on the top, and then you lower the cup, and as the cup goes down, the water starts to fall. And when the water gets to one of these resonant lengths, you can then you can get it such that the water's falling and you hear something like. So when the water is just at the right level, this is essentially one closed end, one open end. Your waveform is forming a maximum amplitude at that open end. You've got a node at the other end. And so by doing this, you can find out what the wavelength is. So you do this, and then there will be another good frequency if you go and have the water even lower. So you have to bring your cup down here, let a bunch of water drain into the cup. And then the wavelength that works, where you're going way down there, and you're letting the water go down. And you have a tuning fork over the opening. I know my picture is not superb, but anyway, then you can use this length as 1/4 of the wavelength, and then you can use this second one as 3/4 of the wavelength. And then if you can measure the frequency of the tuning fork, by the same way that we did in the lab the other week, where you use a microphone and see how quickly the pressure oscillations are going forward. So if you know the frequency and you know essentially the wavelength, then you can effectively measure the speed of sound. Okay, so you get something around, I believe it's 343 meters per second, somewhere in that range. And so that's what this question is about. It's talking about the water level in a vertical glass. And so it is talking about the situation I just described there, where you have a tube and you've got water, and at some heights you're going to be able to fit in a quarter wavelength and then a 3/4 of a wavelength, and so on. Okay, so I'm going to ask you to try to read that question carefully and see if you can work it out. And if you have questions, just let me know, and I will try to go over it in the next video. Another video that I strongly recommend is to search for this James Lincoln tube resonance standing sound waves. He makes extremely good physics demo videos that I've learned some things from. So for instance, here he's doing the thing where he has two open ends and then he puts his hand on the end, and you can hear the frequency go down. So that's a nice demo, and he's got a lot of great demos. So if you're confused by what I've said here, I recommend you go watch James Lincoln's video, because I think he's been more clear than I have been. Now, the thing we are going to do in lab instead of that, we are going to look this week at an LC circuit. And the actual lab we're doing is a little more complicated than what I'm going to tell you about today. But I just want to do the simplest version so that your mind is primed for it. So how does this work? In an LC circuit, it's sort of the simplest oscillating model with electrical components. What you have is just an inductor and a capacitor. Now remember, the energy that an inductor stores is magnetic energy due to the magnetic field in its center. And the amount of energy that it stores is based on the amount of of current that is flowing through it. When you have a current that's going through an inductor, it causes a magnetic field in the middle that stores magnetic energy. On the other hand, a capacitor also can store energy, but the amount of energy that it stores is in the amount of charge that's on its two plates. When the charge builds up, you get an electric field, and the electric field is then holding the energy in the system. So what's interesting about this system is that it essentially can be mapped onto a simple harmonic oscillator, just the same way that a simple harmonic oscillator went between, you remember that was our system where we had a spring and a block, and the block could move back and forth. When the block was moving a lot at the equilibrium position, then the block would have all of the energy, that's kinetic energy. When it's not moving so much and the spring gets stretched one way or the other, in that case you have potential energy of the spring. Now that's a lot like what's happening here. The magnetic energy is a lot like the kinetic energy of this LC circuit, where it's all in the motion of the charges, all in the current, whereas the electrical energy is all in how well the electric field is built up by the stored charge on the two plates. So that would be like the spring getting stretched or squashed. And just to show this qualitatively before I show you quantitatively how to do it, let's say that you start out with a charged capacitor. Well, since it's connected, since the two sides of this capacitor are connected, that is going to want to uncharge. It's going to, the plus, the current is going to want to flow from the plus side, the plus charge side of the capacitor to the minus charge side of the capacitor. And when that happens, that current starts to go through the inductor. But remember, the current, as the current goes through it, this gains magnetic energy. So the energy is leaving the capacitor and going into the inductor. Then, once we get some maximum current going through this, that's the point at which all of our energy is off of our capacitor and all of the energy is on the inductor. As the current continues to flow, why does it continue to flow? Remember that this is an inductor and it wants to keep the status quo. So once the current is flowing, it wants to keep it flowing according to Faraday's law. And so it continues to keep that current flowing, but as this happens, it starts to charge the capacitor the other way. So now we have a plus on the bottom and a minus on the top. And that causes the capacitor now to have some stored energy. In fact, the energy from the system gets dumped into the capacitor to such a point that it eventually will have all of the electrical energy. Now, what's interesting is that going from the capacitor to having all the electrical energy to the capacitor having all the electrical energy again is not one full cycle through the circle. That's the same way that in our our spring and block system, if you had x equals 0, you have an x max and a minus x max. If you're at x max, the spring is holding all of that potential energy. If you're at minus x max, the spring is also holding all the potential energy. But those are two distinct physical situations. In the same way, this is a distinct physical situation from that because we started out with all the plus charge on the top of the capacitor. Now we have all the plus charge on the bottom of the capacitor. And so in the second half of this cycle, the capacitor discharges again, and that current begins to flow the other way through the inductor, which leads the system to have magnetic energy in the inductor instead of electrical energy in the capacitor. And then finally, you get the discharging and you get back to your initial state. Okay, so that's what I've tried to show, what your book tries to show here in this graph, where instead of the electrical and magnetic energies have essentially double the frequency of the system itself. The system goes through some cycle, but the energies are trading off at double that rate. Okay, now tracing this quantitatively, what is the frequency that it takes to make one full oscillation, one full current going this way to current going that way? Well, let's think about it. The inductor, when you put a changing current through it, the change in the current causes an induced voltage. Okay? And in the capacitor, having charge on it produces some voltage. So, because of that, we can do a Kirchhoff loop rule, where the voltages on these two are going to be pointing in opposite directions. But if we do that, if we use these, we can then derive what the frequency should be. So let's just draw this again. We've got our inductor, L, and then we've got our capacitor, C. And what are we've got the voltage of L and the voltage of C. And let's say that we go around the circle like this. We would have our voltage of C, and then the voltage from the L would be in the opposite direction, so it would be minus the voltage of L equals 0. Now, remember our rules here are that Q equals C times V. So that'd be the voltage across the capacitor. So the voltage across the capacitor is going to be Q over C. So this is Q over C. And then the voltage across the inductor is that Faraday's law of voltage. We have that voltage across the capacitor is minus, let's just make sure we're looking at it, minus L di dt. Minus L, that's the inductance of the inductor, di dt. So that's telling us how is the current changing at any given moment. So I have here minus L di dt. Okay, now let's use some physical reasoning. Q and I are not independent of one another. In fact, if I want to connect them, I can use that the change in Q with time is just the current. Now that's useful because then I can put this in terms of current. So to get everything in terms of current, let's go ahead and take the time derivative of both sides of our equation. The time derivative of 0 is just 0. The time derivative of Q is I. So I'm going to have I over C. And then a minus and minus is a plus. And this is going to be L. And then I take the time derivative of di dt, which is the second time derivative of current. And now let's get everything on two different sides. Let's write this in an evocative way. Di squared dt squared equals, and I'm going to subtract this over and divide by L. It's going to be minus 1 over LC times I. Now I want you to notice that this looks a lot like the form that we found for an oscillating, a simple harmonic oscillator. It looked like this. And why is this a familiar form? It's because if I have any x that has the form, like any x, or in this case it would be like I, is some I max times cosine omega t. So if I have that kind of sinusoidal dependence, then I would just get my d squared I dt squared equals minus omega squared times I. So if you have this form, you will get an extra factor of omega squared out front. So what I can do is I can identify this as my omega squared. And so that omega squared equals 1 over LC. Or if I take the square root of both sides, my frequency with which this goes through one full cycle. So that's you start out with this plus charged up. The plus goes to the other side, and the plus charge comes back. That's one full cycle. And the omega is 2 pi, is square root of LC, which of course is the same as 2 pi times the frequency, or 2 pi over the period. Okay, so this is going to be very important because we can actually measure that LC, and what's interesting, of course, is that you really can go pretty well. The capacitor is like the spring, the inductor is like the block, the electrical energy is like the potential energy, the magnetic energy is like the kinetic energy, and the velocity of the block is like the current. And in that way, you're sort of mapping one system onto the other. And so if you look at this in the lab, there's going to be some sort of resistance in your wires, and so instead of just going back and forth forever, the current eventually dies off. But we're going to be looking at something like this in lab this week. So stay tuned for that, and we'll discuss more about it next time. Just to remark again, this week your homework is due on Friday, and you really should be able to get almost all of it done with just what we've done today here in class. So for instance, one of the questions I gave you is, in an oscillating LC circuit, you have an L of 1.10 millihenries. So L equals 1.1 times 10 to the minus 3 henries. And then a C of 4 microfarads, say, so 4.0 times 10 to the minus 6 farads. The maximum charge on the capacitor is 3 microcoulombs. Okay, so they give you that Q is 3 times 10 to the minus 6 coulombs, and then it says find the maximum current. Okay, so my hint to you on this type of a question is that if they give you the maximum charge, they have given you essentially the maximum electric energy. But they want you to find the maximum current. The maximum current is going to occur when you have all of that energy having been transferred over into magnetic energy. So you're going to be able to solve this by saying the amount of energy that's maximal in the electrical energy is going to be the same as the amount of maximal energy in the magnetic domain. So you're going to set those two equal to each other. And you know L, you know C, you know Q, and they are asking you to find I. Okay, so I think you can do that. All right, so we have gone over quite a bit today. We've talked about how waves traveling in opposite directions can set up standing waves with nodes and antinodes. We've talked about how the resonant frequencies of a pipe or a string can be found by considering the nodes and antinodes. And then we've talked about how a capacitor and an inductor in series can be set up to trade their energy back and forth, just like a block and a spring in a simple harmonic oscillator.